Hi everyone and welcome to this video. Last time we have discussed about Hopfield networks and how to use them to behave as analog digital converters. This time we are going to go on a different topic that still use neural networks, but we are going to do something different. What we are going to do in this video essentially is this. We are going to do a quick recap on feedforward neural networks and a quick recap on the training phase of neural networks. And then we are going to see that this is very close to an optimization problem. This is actually an optimization problem. And then we are going to introduce the genetic algorithms because we want to use a genetic algorithm to train a neural network. And what we are going to do at the very end is we are going to implement a genetic algorithm that can train a neural network, and all of these in BASIC. So the neural network at the end will be capable of perform a task, and the training and the inference will all happen in BASIC. We are going to use, as usual, the Atari BASIC for this task. So, as usual, I'm reporting here two links that you can use if you want to have, let's say, the software infrastructure that I am using here to show the implementation that I have implemented that I am going to explain here. There is also a useful article that I am sharing, which is an article coming from Wikipedia, which is on genetic algorithms. So if you are not very familiar with this topic, you can go there and you can have a look at it. It will provide more details that I am going to provide in this video. But the amount of details that I will provide should be actually enough to implement the training of a neural network in BASIC. If you haven't seen this video before, I have previously posted a video on feedforward neural networks. There is a link here that I am going to report in the description below. And as usual, I want to thank you all for being here, for following these videos, for continuing to subscribe, leaving comments, giving thumbs up. This is very encouraging. So thank you very much about this. So what is a feedforward neural network? I'm showing this picture here, this figure that shows a quintessential feedforward neural network. And to recap quickly, you can think of this as an ensemble of artificial neurons that are shown here in circles, and these artificial neurons are connected with each other. So at the end, if you connect them in the way it is now, you end up having several layers. You have a layer that is the input layer, which is represented here by one neuron that is in blue. Then you have a hidden layer, which is the one in the middle that is represented by these four neurons that are in green. And finally, you have an output layer that is represented by this single neuron that is in red. And what happens is that all these neurons are connected with each other, and the strength of the connection is represented by a real number that we call a weight. So in practice, what you will have here is this structure that is going to process information. If you give a value x to the input neuron, this is going to propagate over the hidden neurons that you have in the hidden layer. And then eventually this information is going to be processed on the hidden layer. The information is going to propagate over the output layer, and again the information is going to be processed by the output layer. So essentially this is what we mean by a feedforward neural network. Now we are going to see how we train those feedforward neural networks. To train a neural network, we need more or less four main components, and these four components are shown here in the figure that you see on the screen. The first thing that one needs is a data set. What do we mean by a data set? Essentially, we mean some sort of relation between an input and an output. So here, this is shown in terms of a set of two numbers, xi and yi, and you can think of yi being some label or some number that is attached to the value xi, or something that corresponds to the value xi. And you can have a certain number of these samples. This is how they are called, and you can have, for example, n d of these samples. Then the second component that we see here is the model. We need a model to train. Usually a model is a mathematical function that depends on the input, and it's going to provide an output, but it's also a parameterized mathematical function. So it means that the output value that you are going to get depends on some parameters. In the specific case of artificial neural networks, which is what we are going to treat here in this video, the parameters that the network depends on are weights and biases, which we are showing here. We are representing them as the symbol W and the symbol B. You also have to think that W and B here are set of values, so you can think of them, for example, as matrices or as vectors. And for example, you can think of the weights as a matrix of values, and you can think of the biases as a vector of values. So the model has to be specified by some function. In our particular case here, this is the artificial neural network. The third component that is important to have in the training phase is the loss function, also called the objective function. And you have to think of these as some sort of mathematical concept of a distance. And the distance is between your data set and the predictions that your model can perform. So you want the predictions to be very, very close to the data set, so to the observations that these samples are providing. You want this distance to be as minimal as possible. So the loss function here is called L, and in a very symbolic way we show that it depends, of course, on the model, so which is net of xi wb, and it also depends on the data, which in this case is xi and yi. So this is an actual distance between the network or the model and the data that we have at hand. The last component is the minimization, which means that in practice we need to have some method that can minimize the loss function. This is exactly what we do in a training phase. Usually in the mainstream we use backpropagation along with stochastic gradient descent, and you can think of these two approaches as one approach, where essentially this approach tells you how to compute the gradient and how to use the gradient of the loss function in order to minimize the loss function itself. So this is the mainstream approach that is used in the machine learning community. This method shows to work very well, but it consumes a lot of memory, especially backpropagation. In order to reconstruct the gradient of the loss function, it requires some memory. So we are going to use a different method that I'm going to introduce right now. We just saw that a training phase, or let's say the training method, is essentially an optimization method, and the problem of training a machine learning model, or the problem of training a neural network, is essentially an optimization problem. So rather than using mainstream methods that might not be capable of running on, let's say, very limited, in a very limited environment like an 8-bit computer, we are going to use something different that do not require this amount of memory. And the method that we are going to use in this video is a genetic algorithm. This is exactly what we are going to use to minimize the loss function of the problem. So what is a genetic algorithm? This is actually very easy to explain. You start from some solution of your problem. So in our case, it could be, for example, a set of weights and biases. And the way you start is by just giving some random values if you don't have any educated guess. But if you do have some educated guess, then you can use that guess. But you have to start from something where you are not really sure how close it is to the actual solution that you are looking for. And then the second step becomes an evaluation of the solution that you have at hand. The evaluation can happen, for example, by using an objective function which corresponds to some sort of distance between your model and the data that you have at hand. You can evaluate this solution by using this objective function or the loss function, and then you can start to ask the question, is this solution good enough? If the solution is good enough, which means that, for example, your objective function has gone to a value, has now a value that is lower than some threshold, then you already have your solution and you can stop the algorithm. If that solution is not good enough, let's say, for example, because the objective function has a value that is above a certain threshold, then you mutate the solution and you continue evaluating the solution until this loop between evaluation and mutation goes to a convergence and the solution becomes good enough that you can stop the algorithm. A few words about the mutation. This can happen more or less in many different ways. The way we are going to do is a random mutation in the basic code because this is something very, very simple to obtain, and yet it's very, very efficient. So this will be the criterion that we are going to use to mutate the solution in our particular case. So let's now see how the implementation works. Before we go through the implementation of a genetic algorithm to train the neural network, I'm going to spend a few words on the actual problem that we are solving here. And I have this figure that you see on the screen which simplifies this discussion. So in practice, what we are going to do is the following problem. We suppose that we have a function, which is this function that you see here in blue, so fx equal x squared. And what we are going to do is we are going to take 3 different points of this function. So these are the red dots that you see here on the screen, which this means in practice that we are going to end up having a set of points. So we are going to have, let's say, a set of couples of real numbers. So every time we have a point, we have x1, y1, x2, y2, x3, y3, and so on. And we are going to take only 3 points here. So the first point, so the first coordinate of these points will represent the x of the point, so the x coordinate, and the second is going to represent the y coordinate. But you also can interpret these as the input to a model, so the x will be the input and the y becomes the output of the model that you would like to have. So all of a sudden this set of points becomes a data set. And this is the data set that we are going to use. So the problem that we are going to solve here consists in creating a neural network that is capable of predicting points of the function that we have at hand here, which is f of x equal x squared. So I'm going to go now through the listing of the program so that everything becomes very, very clear. The list of the program I have prepared is the following one, so I'm going to show it to you so that you can stop this video anytime and have a look at it. But we are also going to go through parts of this code. So the first part is consists between line 10 to line 16, and these are the lines of the code. So what we have here essentially is a few definitions. We are going to define a few constants, for example the p number that you see here on line 13, and we are going to define other constants that are useful when we train the neural network. So on line 14, when you see here iter, this would be the total number of iterations for the genetic algorithm, so in this case 32. The value f here, this variable f, this is a factor that is equal to 2.5. This is a factor that we are going to reduce with time, and this is a factor that we are going to use every time we mutate the solution that we have at hand. F and df are going to be what we need, and in practice df is going to be the decrement of f. So at every iteration of the genetic algorithm, f will be decreased by a quantity df, and we will use the factor f to mutate the solution. You are going to see this in a few next lines. This will become very clear. On line 15, we start to define a few values for the neural network. NH equal 4, this is the total number of hidden neurons that we have in the network. NN then becomes the total number of neurons in the network, excluding the input neuron. So in this case, since we have only one output neuron, this will be NH plus 1. NP equal 3, this is the total number of points we are going to use for this curve fitting experiment that we are going to perform, and NW, this is the number of weights that we have in the network. I am taking for granted that all the biases in this network will be equal to 0, so that's why we don't have any variable called NB where we have the total number of biases, because we just take them for granted being equal to 0. And then eventually we have here another few variables, especially here the most important ones are dx and db. You are going to understand what they mean once we go through other parts of the code. So if we now continue and go from line 21 till 25, this is what we get. So now here we are defining the data set that we are going to use, which consists in 3 points, and these points will have coordinates, so we will call them x0 and y0, and they will have an index I that goes from 1 to np, where np is equal to 3. And what we are doing here is essentially 23, we define an x axis, or let's say we define a value over the x axis, and on line 24 we define a value on the y-axis which correspond to the square of the value x0. So this is practically the function f of x equal x squared. So now if we continue with the code, we can go from line 30 to line 32, where here now we start to define some initial value, or let's say we provide an initial guess of the weights that the genetic algorithm is going to try to optimize. So in this particular case, as you can see, we do something extremely simple, which corresponds in practically providing a random value that is going to be between 0 and 1. So if we now continue with this code, we can show line 35 very quickly. So this is just a remark, and this remark practically says that this is where the genetic algorithm starts. So if we now go slightly ahead and we go from line 40 to line 95, this is where we practically see the whole algorithm being implemented. So this is the genetic algorithm. And the loop that you see here from line 40 to line 90, this is the main loop. This is the loop that goes through every iteration of the genetic algorithm. So the very first thing that we do on line 44, we take the best solution that we have found so far, which correspond in this case to the array WB. DB and we mutate it. The way we mutate it is actually very simple. We take a random number, so we take the original value of the weight and then we take a random number between 0 and 1 and we multiply it by a factor f, and this is added to the original value of the weight. So this is a stochastic way of mutating the weights. This is definitely not the smartest way, but this is definitely also a way that works and that you can implement on an 8-bit machine or on any machine that is very limited in computational resources. So if we now go through the rest of this part of the code, from line 50 more or less until line 77, what we do here is that we perform the inference of the neural network. So we perform this inference and we do this for every point of the data set. And every time we compute the inference of this network, what we do is also on line 76, we compute the loss function. So the loss function in this case is going to be a distance between the prediction and the actual value of the curve. And we practically do this, we make a sum of the square of these distances, and then eventually at the end on line 78 we take the average of this sum and we make the square root. So this becomes an L2 norm. As you can see here on line 80, if the value of dB is bigger than the actual distance that we have so far, so this means that now we have found a better solution, so we want to store it. So we have to do a go sub to line 100, and we are going now to list lines from 100 to line 110, where practically this is where we store the best solution. So every time we find a better set of weights, what we are going to do here in this part of the code is that we are going to store this best set of weights somewhere, and this is represented by the array WB, and then we are going to use it. And as you can see on line 107, what we get here is also we update the factor f that is useful for the mutation of the solution that we have at hand. So we are now ready to run this code, which we are going to do right away, and this is what we are going to see. So we are going to run this, and of course the initial guess that we have is a random guess. So when we are going to print the value of the loss function every time per iteration, what we are going to see is that the loss function should have a value that decreases in time. So I'm going to hit enter here and see what happens. And of course this takes some time, but as you can see here on the right hand side, this is where we are showing the best value that we have found for the loss function so far, and clearly you can see that it started from a very high value and this value is now getting lower. So it went from practically 0.66 as you can see, and now it seems that it is settling down to a value that is 0.32 or 32. So of course this is a stochastic approach, which means that if I rerun it, I'm going to obtain something different. And as you can see here now, those values are different from the previous run that we have done. So far it seems that the loss function is settling down on a value that is 0.41, which is very, very different from the previous run that we have done. We are going to let this run go till the end, and then we are going to rerun for last time this code so that we can see that the result is once again different. So let's run it again just to see what happens this time. And as you can see, this time things are going different again. So now we are hitting a value that is 0.22, which is much lower than the previous one that we got in the previous run. So the main idea here and the main, let's say, lesson that we get from this is that genetic algorithms can run on 8-bit machines. It does run on the Atari 800. They can be used to train neural network in a very efficient way, but it is a stochastic approach. So it means that you will have to run this code many times until you find the value of a loss function that you actually want to obtain. Of course, 32 iterations is not so big, so you would have to run this for much more iterations. I would suggest a few hundred. And actually, I would suggest you to do this as an exercise to see what happens when you run this for much more iterations. So this concludes this video for today. As always, I want to thank you for being here, and I want to thank you for your attention, and I hope to see you in the next one.